Okay, so my apologies for the video cutting out the tail end of part A of 1.7. My iPad, I think something crashed on me. I'm not quite sure I understand what happened, but anyway, so where we left off, I was getting ready to discuss. We had discussed basically linear independence, dependence with sets of one vector. We discussed it with the zero vector. We discussed it with the unit vector. I wanted to get into a set containing two vectors, right? So if a set contains two vectors, now two vectors, how would we discuss linear independence versus linear dependence? Again, if you're calling upon your notes, just recall that we say it's linearly independent if the only way to arrive at zero is by choosing scalar weights of zero. But if there are other ways, other linear combinations, ways of getting to zero, then we would say, my apologies, I circled independent. So independent would be only the trivial solution, only weights of zero. We would say linearly dependent if there are other scalar weights that can be used to get to zero, okay? So what I'm going to do before I answer this question about a set of two vectors is I want to look at a problem. So example 3. So notice we have part A, part B, and the question in front of us is to determine if the following sets of two vectors are linearly independent. So notice for part A, you have two vectors, v1, v2, which is defined as 3, 1, and v2 is defined as 6, 2. Whereas part B, very similar, except v sub 1 is 3, 2, not 3, 1, but v sub 2 is the same. Now, the subtle difference does make a difference when determining whether only has the trivial solution or not. The geometry can help. So for example, if you were to plot the vector 3, 1, right? So you can imagine going over 3 up 1. And then if you were to plot, so again, a lot of times the geometry really can help make the point. So over 3 up 1, so there's vector v sub 1. Now if we were to go over 6 up 2, that would be your vector v sub 2. Notice something. Notice that v sub 1 and v sub 2 both lie on the same line running through the origin, right? In other words, there is a way, I think you would agree with me here, that there is a way that I should be able to scale v sub 1. There's some number that I multiply v sub 1 by in order to arrive at v sub 2. And it's fairly easy to spot it, right? If you were to double v sub 1, right, you would get v sub 2. Right? 2 times 3 is 6, 2 times 1 is 2. So what we would say is that v sub 1 and v sub 2 are scalar multiples. I want to say that again. So the idea of scalar multiples means that you can scale one vector to turn it into another vector. Now, let's look at the exact same geometry with part B. So now we're going to go over 3 up 2. So that is how we get our v sub 1, and then we would go over 6 up 2. And that is how we would get our v sub 2. And notice for a second that there is no scalar out there. So if you think of some scalar times v sub 1 equals v sub 2, there is no scalar out there such that you can turn one vector into the other. What you can do now, listen, many of you are savvy and you can just see, you can just spot it. That, hey, like for example, many of you just spotted that 2 times v sub 1 equals v sub 2. But what I'm going to do is I just want to show you that how you could be sure, like say if it were a homework quiz test, something like that. So what you can do is, we'll start with part B. We're going to set our components equal to each other. And then what we're going to do is we're going to assign a scalar to one of the vectors, v sub 1 or v sub 2. Doesn't matter, just as long if you assign a scalar to 3 here, you want to make sure you assign the scalar to 2 here, okay? Because we're just going to set component equal to component. Now, if I solve for c, right, divide both sides by 3, divide both sides by 2, we see that c is equal to 2 here, whereas c is equal to 1 here. In other words, I could get v sub 1 to become v sub 2 if I could scale the 3 by 2 and scale the 2 by 1, but that's not how scaling works, right? Either I scale the whole vector or I do not. I don't get to scale just one component of the vector. So notice that these values don't equal to each other. So therefore, these two vectors are not scalar multiples. If you did the same thing over here, notice that if I won't write it, but imagine if you had, c3 equals 6, and then c1 equals 2. If you would solve and you would see that c is equal to 2 for both. So you got the same c value, the same scalar for both, whereas over here you do not. So at this stage, geometrically, you can see that scalar multiples are vectors that reside on the same line running through the origin here, whereas non-scalar multiple vectors, the only point that I think you'll agree with me, the only point that these two vectors have in common is they both go through the origin, right? They both go through 0, 0. Whereas these vectors have an infinite amount of points in common. Okay, now, how does this, two things. How does this topic turn into a conversation about linear dependence and independence? And two, what is a way of being able to tell them, or what's another way of being able to tell the answer to these questions if you can't spot the scalar multiple part? So let me answer the former first. So what we can write is, if they are scalar multiples, if you have a set of two vectors that are scalar multiples, then what you have is linear dependence. Now, this is somewhat sloppy, right? I mean, you would want to make sure that I'm just speaking based on these two scalar multiples. I should refine this a little bit better, but just speaking informally, you can imagine setting these two vectors up as a vector equation. So what I'm going to do really quickly so you can see it is I'm going to plug v sub 1 here, I'm going to plug v sub 2 here. So that gives me x sub 1 times 3, 1, plus x sub 2 times 6, 2. And then I'm going to write 0 as the 0 vector in the context of this problem. Now, you can imagine that the game that we would be playing is, what scalars could you use such that this linear combination is equal to 0? Now, we know that if I choose 0 for x sub 1 and I choose 0 for x sub 2, we know that that would work. Remember, that's the trivial solution. The question is, are there others aside from just choosing scalars of 0, right? 0 plus 0, of course, is 0. And I think you would agree, when they're linear combinations, like when they're scalar multiples like this, I'm saying, you could let x sub 1, say, equal -2, and you could let x sub 2 equal 1, and then think about what you would have at that point. You would have -2 times 3, 1, plus 1 times 6, 2, right? Which would end up giving you -6, -2, plus 6, 2, which indeed does get you to the 0 vector, 0, 0. So clearly there is more than one way to get a solution to this equation. And so scalar multiples, you can see that you have more than just the trivial solution, so therefore linear dependence. In this case over here, so these are non-scalar multiples. And what you're going to find is the only way to make this equation equal 0 is if you were to choose the trivial solution. This is the only way to make this a true statement. Okay, so back to this, I'm going to go back to the previous page. Let's go ahead and answer that question. So scalar multiples, linear dependence. Ready? So a set containing 2 vectors is linearly what? As long as they are scalar multiples of each other. So if they are scalar multiples, right? Here on the previous page. So if they are scalar multiples, then we have linear dependence. However, if you have a set of 2 vectors, is linearly what? As long as they are not scalar multiples of each other. So if the 2 vectors are not scalar multiples, just like over here, then the only point that they share in common is 0, 0, which is our trivial solution. So this would be linearly independent. Okay, so the answer to the question, determine if the following sets are linearly independent. Well, part A would be they are not linearly independent. Part B would be they are linearly independent. Okay, so to generalize this, because we've talked about two sets of one vectors, 2 vectors, etc. So what we're going to do is we want to try to generalize this statement. So to make sure you understand what this is saying, we're going to let P be the number of vectors. Right? So P is the number of vectors. Now, notice that Rn, which would be the dimension, the space that you are residing in Rn, let me write it this way. So in Rn, the n, right, the n part of Rn, well, let's think about it. R2, that would be a plane, right, 2 dimensions. R3 would be space, 3 dimensions. So notice that the n ends up becoming your rows, whereas the vectors is your columns. So in this case, the n, there's a few ways of thinking about this. Let me explain it in the language of vectors first. So in this case, the n is equal to, so I'll do it this way. P is the number of vectors, which is equal to the number of columns. All right, and your n, in this case, is the number of rows. Now, so that we can generalize these ideas, if you have 50 vectors or 10 vectors or 2 vectors, what we're going to do is we're going to compare the number of columns to the number of rows. So in each of these statements, it reads a set containing blank vectors. Now remember, we're going to let P equal the number of vectors. And again, you can see how when you have a vector, like if you had 2, 2, 2, that would end up becoming one of the columns of your matrix. So our set contains P vectors. Now, is linearly what? Well, independent, dependent, and here it is, if the number of vectors in the set is greater than n. All right, so I'll come back to this part. So the number of vectors in the set is greater than n. I just want to make sure you understand that if P is the number of vectors, they're saying if it's greater than n. Now that's kind of what you have here, right? If you think about it. So this would be 1, 2, 3, 4, 5 vectors. P is equal to 5 in this case. Assuming this is I don't know, I assume this is a coefficient matrix. But the number of n, in this case, the number of rows is 3. 1, 2, 3. So clearly, in this case, P is greater than n. The number of vectors is greater than the number of rows. But what do we get to say, right? So what is it that we get to say when that's the case, when the number of vectors is greater than the number of rows? Well, now I'll read the definition. If a set contains more vectors than entries in each vector, then the set is linearly dependent. So in other words, if P is greater than n, the columns are linearly dependent. Right? I'll tell you what, let me not address this. Let me not address this just in case. There's a little caveat I want to talk about. But let me really try to make sure you understand this part, because you don't want just another idea, another thing to memorize. Let me turn this into language that you already know. So instead of calling them rows and columns, let's talk about the rows as the equations. And let's talk about the columns as the number of variables. right? So you can imagine for just a second, I'm just going to grab one, let's do it, use a different color here. Let's just look at one of these rows. All right, so row 1. So I grant you that they don't tell us what the inputs are, right? The elements, they just give us 5 stars. But to make sure you understand, each of these stars would represent what? It would represent some variable. So you could think of like X, Y, Z, W, V, right? So if this is a coefficient matrix, you would have 1, 2, 3, 4, 5 variables. And of course, this is just row 1, so this would just, each row is its own equation. So will you grant me that looking at this matrix up here, this matrix has 3 equations, 5 variables. If you don't see this, I need you to see it. So row 1, equation 1. Row 2, equation 2. Row 3, equation 3. 3 equations. 1, 2, 3, 4, 5 variables. If you have more variables, than equations, then you're going to have free variables. If you have free variables, you're going to have linear dependence. I hope that helps connect the idea of the number of vectors. So let me go ahead and do one more, and then we'll conclude this section. And I'm just going to do it in this video. So there's should only be 2 parts, part A, part B, to this section. But let's try example. I'll come back to this if I need to in just a second. But let me see if I can bring some of these definitions to life through an example. So notice they define vector u and vector v. So let's go ahead and start collecting some information. So you agree with me that P, the number of vectors given to us, is 2. Now, I think you'll also agree with me that each of these vectors has 3 entries, right? So the n, or the Rn, the space that we are residing in, is equal to 3. Right? So you can think of x over 3, then over y, then up 0. Notice that you could think of the z part as being 0 here. So right away, let's before I've even read the question, let's go ahead and take notice that n is greater than p, right? So n is greater than p. Okay. So if that's the case, so n is 3. Yes, so n is greater than p. So based off what we've started to conclude, we could say that if the number of vectors is larger than the number of entries per vector, right? So p is 5. 5 is bigger than 3. So, all right, so we can't really determine linear dependence and dependence yet, right? We got p is great. We got a statement about p greater than n. We don't have a statement about n greater than p. Okay. All right. Now let me see if I can continue with the question. So, given the following 2 vectors, we want to describe the set spanned by u and v. And again, if this language is starting to build up, you know, if you're just confused, it's that you're letting the language build up is what I really mean. So when we say spanned, let's make sure we truly understand what we're saying when we talk about the set spanned by u and v. So this is what it means. Recall that a linear combination right? Let's think of it as a game. Here's the game. You're given two vectors, u and v. And then you're given two scalars, x sub 1 and x sub 2. And the only thing you can do is scale and add. So you can scale your vectors and you can add your vectors. Those are the only two options. Do you understand the rules? Scale and add is the only thing you can do. The question is, given those two operations, what other vectors can you reach? Right? Can you reach, for example, 0, 0? Well, yeah, sure. If I just chose a 0 for x1, 0 for x2, of course I could get to 0, 0. So we would say that the 0, 0 is in the span of those two vectors. I can get to 0. But you got to think about, can I get to any other vector? Right? Think of, let's see if we can write it this way. Let's let this vector A, B, C. Let's let that vector represent every single point in space. Every length, width, height. Over 2, up 2, length, width, height, 3, 0, 0, 1. Every single point in space, we're going to let this vector ABC represent every point in R3. Now, our question is, describe the set spanned by u and v. Describe the set spanned by u and v. Now, the first thing we would want to know, remember when we were talking about a set of two vectors? The first thing we would want to know is, are they scalar multiples? Right, before I start trying to describe the set. By set, they mean describe all the vectors that you can get through a linear combination. That's what set spanned would translate to be. But nevertheless, before I talk about the set that's spanned by u and v, let's talk about u and v. Is there some relationship of u and v? In other words, is it possible to scale u and turn it into v? For example, 2u, does 2u equal v? Or a negative 2u, etc. Well, recall that you can always do that by let's just take each entry of u, so 3, 1, 0, and we're going to attach the same scalar c to each of them. And we're just going to set each component equal to each other. So the 3 is going to be set equal to the 1. The 1 is going to be set equal to the 6, and the 0 is going to be set equal to the 0. And all we're going to do at this point is just solve for c. So c equals 0, c equals 6, c equals 1/3. Notice that the scalar is different, so I can't do it. I mean, I could scale if you would allow me to scale this component by 1/3 and this component by 6 and this component by 0, then I could get u to equal v. But there's no scalar, there's absolutely no scalar, single scalar that allows u to become v. So these are definitely not equal to each other. They're not scalar multiples. Okay, so this statement right here, they are not scalar multiples. All right, so that tells me something. So if we look at just the geometry of that, forget about that W for a second. So here's your U, here's your V. So if I were going to try to describe the set spanned by U and V, first thing I would want to point out is notice that each vector, U and V, both of them have 0 in their Z component, right? Or I could say, for you engineers, IJK. So they have 0 for their Z variable, or 0 for their K component, I guess is a better way of saying it. So even though the vector is in 3 dimensions, really if you think of just some plane, some 2-dimensional plane, really, since you don't have a 0 here for the Z variable or K component, there's no way for you to leave that plane, right? So U resides in this plane, so does V resides in this plane. So if I was trying to describe the set spanned by U and V, I would say that it's the set of vectors such that they reside on the x1, x2 plane. Let me write that for you. So how would that, in other words, let me put this into the language that you would write, say, on a test or on the homework. So the span of vector U and vector V can be described as a plane, an x1, x2 plane. Okay, now, furthermore, the question says, and explain why some vector W is in the span of U and V if and only if the set UVW is linearly dependent. Well, let's think of the best way to try to explain that to you. So I think we'll start with the geometry. So to say that W is in the span, again, please, I know the video's been going for a while. I know you're getting tired. Listen to my words. If vector W is in the span of U and V, that means, with me, that means you can use these two vectors to arrive at W. How about this? See this? Look at this graph. Come back to me. Do you see how you will never get to this point W by scaling and adding U and V? You can never get here, right? There's just no way for you to get to this point W. So in this picture, W is not in the span. In this picture, W is in the span. What's the difference? The difference is, in this picture, you can arrive at W through some linear combination. In this picture, you cannot arrive at W through some linear combination. So what does that mean in terms of dependence, independence? So what does it mean in terms of, the geometry just speaks volumes, right? It's, in this particular case, W is in the span of U and V. So that must mean, right, if and only if U, W, and V there must be some linear dependence here. In this second picture, W is not in the span of U and V. You cannot get W from linear combinations of U and V. So if it's not in the span, W is not in the span of U and V, then UV, the set of UVW must be linearly independent. I hope that makes sense. I'll try one more time. Well, no, I hope that makes sense. That this discussion of dependence, independence, again, it's just another way of looking at the homogeneous equations, and it's just another way of discussing trivial solutions. Only now we're looking at it from the standpoint of a vector and a vector equation, as opposed to a matrix equation. Nevertheless, I hope this helps, and I will see you in another video.